For the first time, scientists have studied the magnetic field of a black hole inside the Milky Way in multiple wavelengths and found that it doesn't conform to what we previously thought. According to researchers at the University of Florida and the University of Texas at San Antonio, the black hole called V404 Cygni's magnetic field is much weaker than expected, a discovery that means we may have to rework our current models for black hole jets. V404 Cygni, located around 7,800 light-years away in the constellation of Cygnus, is a binary microquasar system consisting of a black hole about 9 times the mass of the Sun, and its companion star, an early red giant slightly smaller than the Sun. In 2015, the system flared into life, and, over the course of about a week, periodically flashed with activity as the black hole devoured material from its companion star. At times, it was the brightest X-ray object in the sky, but it also showed, according to NASA Goddard's Eleanor Troja, exceptional variation at all wavelengths, offering a rare opportunity to study both V404 Cygni and black hole feeding activity. It was this period that the team, led by Yigal Dalila at the University of Florida, studied. Where black holes are active, they become surrounded by a brightly glowing accretion disk, lit by the gravitational and frictional forces that heat the material as it swirls towards the black hole. As they consume matter, black holes expel powerful jets of plasma at near light speed from the coronae regions of hot, swirling gas above and below the accretion disk. Previous research has shown that these coronae and the jets are controlled by powerful magnetic fields, and the stronger the magnetic fields close to the black hole's event horizon, the brighter its jets. This is because the magnetic fields are thought to act like a synchrotron, accelerating the particles that travel through it. Dalila's team studied V404 Cygni's 2015 feeding event across optical, infrared, X-ray and radio wavelengths, and found rapid synchrotron cooling events that allowed them to obtain a precise measurement of the magnetic field. Their data revealed a much weaker magnetic field than predicted by current models. These models typically talk about much larger magnetic fields at the base of the jet, which many assume to be equivalent to the corona, Dalila told Newsweek. Our results indicate that these models might be oversimplified. Specifically, there may not be a single magnetic field value for each black hole. Black holes themselves don't have magnetic poles, and therefore don't generate magnetic fields. This means that the accretion disk corona magnetic fields are somehow generated by the space around a black hole, a process that is not well understood at this point. This result doesn't mean that previous findings showing strong magnetic fields are incorrect, but it does suggest that the dynamics may be a little more complicated than previously thought. The team's research did find that synchrotron processes dominated the cooling events, but could not provide data on what caused the particles to accelerate in the first place. It is, as one has come to expect from black holes, a finding that answers one question and turns up a lot more in need of further research. We need to understand black holes in general, said researcher Chris Packham of the University of Texas at San Antonio. If we go back to the very earliest point in our universe, just after the Big Bang, there seems to have always been a strong correlation between black holes and galaxies. It seems that the birth and evolution of black holes and galaxies, our cosmic island, are intimately linked. Our results are surprising and one that we're still trying to puzzle out. The research has been published in the journal Science.